Okay, so this is a very highly theoretical talk, and I want to show that for some natural, very general learning problem, there can be no dimension that characterizes this problem. So the luckiness that we have is VC dimension or fat shattering dimension, all kind of things, no dimension will be able to do it. So what is the problem? It's a very general learning problem. You have a collection of real valued functions, or if you want random variables or queries, and you get a sample from an unknown distribution, and you want to know which of those random variables will get the highest value, the highest expectation under this unknown probability distribution. So that's a very general question. You want to know which random variable does the best. Here are some examples of things that can be cast as such a problem. So binary classification, say the random variables are the error of your different h's, and you want to find which h will give you the minimum error under the unknown distribution. Or multi-class prediction, or k-center clustering. So your model is a set of k-centers, and you want to know on the unknown distribution which of them will give you the minimum k-means cost, and so on. So many learning problems can be cast as this general problem of find the random variable of minimum or maximum expectation under an unknown distribution. So this was already realized by Vapnik. It's a Vapnik general statistical model, and Vapnik already asked, can we characterize it by a dimension? And we will show that this is just impossible. So our goal is to characterize which class are EMX learnable. So EMX here is for expectation maximization. And we ask, can we have a purely combinatorial characterization of the classes that are learnable, just like we have with the VC dimension of binary classification. So I will focus on a concrete case. So assume that you have just a domain and a collection of subsets of this domain, and there's an unknown distribution, and you want to know which of these subsets has the highest expectation of being hit by this probability. So you have a collection of subsets. You want to know which of them has the highest weight under the unknown probability distribution. And you want to find it only based on the sample from this unknown distribution. So if we look at generally the tools that we are using in machine learning, we have the notion of pack learnability. And we have, in the case of binary classification, we can show that all of these are equivalent. Pack learnability, learning with empirical risk minimization, weak learnability, uniform convergence, existence of compression schemes, and finiteness of the VC dimension. So all of those are known to be equivalent for the case of binary classification. For our problem, only the blue ones are equivalent, so we can show that learnability of this problem is equivalent to weak learnability, and we came up with a notion of compression scheme that is equivalent to this learnability. But what I want to focus on is a VC dimension. Is there a dimension that characterizes it? So we have here a theorem which is completely surprising, that this problem is tightly dependent on the continuum hypothesis, and that a certain problem here is learnable if and only if the continuum is less than aleph omega. This is complete set theory. On the face of it, it's completely unrelated. But the main point is that we show here that learnability depends on the continuum hypothesis. The continuum hypothesis is independent of set theory. Therefore, we have here a problem such that the question whether it's learnable or not is independent of set theory. And as a corollary, we can get that there can be no dimension in a very precise sense that characterizes this problem, because the dimension of a class will not change between one model of set theory to another model of set theory. But here the learnability does change between one model of set theory and another. So we have a strange tool going through set theory showing you that for this basic learning problem, there can be no dimension that will characterize it. One can ask, how come we get independence of set theory? And I think here is a very interesting question. When Vapnik defined the notion of learnability and proved this beautiful characterization, he defined learnability in terms of the existence of learning function. And that's where the independence comes in. We can try to redefine learnability by requiring that the learner is an algorithm. not a function, not arbitrary function, but the algorithm. And it turns out in recent work that once we define learnability in terms of algorithm rather than functions, then all the classical results collapse. So we can have classes of small VC dimension which are not learnable. It's an interesting area to investigate what characterizes learnability when we require the learner to be an algorithm. Thank you. Yeah, so there is an archive paper, and there is also a Nature paper on this, which just tells the story in a sexy way.
Let's thank Shai again.